Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Polar Coordinates, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing the definition of polar coordinates, plotting polar coordinates, converting between polar and rectangular coordinates, polar equations, the arc length of a circle defined by polar coordinates, and the area of a region defined by polar coordinates. In the rectangular coordinate system, there are two perpendicular axes, x-axis and y-axis. The point of intersection is called the origin. A polar coordinate system is constructed with a similar origin called the pole, with points described by the angle theta from the x-axis and the distance from the pole r, or radius. In trigonometry, we combined the radius on the xy coordinate plane and derived other equations. First, the Pythagorean theorem, which gives us x squared plus y squared equals r squared. Next, our trig functions. Sine theta equals the opposite side over the hypotenuse, or y over r. From this, we can solve for y, giving us y equals r sine theta. Next, cosine theta equals the adjacent side over the hypotenuse, or x over r, which can be solved for x, giving us x equals r cosine theta. Finally, tangent theta equals the opposite over the adjacent, or y over x. To plot a point on a polar grid coordinate system, we take the angle from the x-axis and the distance from the origin. For example, r theta equals 2 pi over 3. In this case, plot the angle, pi over 3, from the x-axis and move out from the origin the amount of the r value, in this case 2 units. If P is a point with coordinates r theta, then the rectangular coordinates xy of P are given by x equals r cosine theta and y equals r sine theta. If we start with a point in polar coordinates like 2 pi over 3, the conversion is simply based on these trigonometric equations that you have already learned. In this case, x is equal to 2 cosine pi over 3. Cosine pi over 3 is 1/2, so x equals 1. Y is equal to 2 sine pi over 3. Sine pi over 3 is equal to the square root of 3 over 2. So in this case, y is equal to the square root of 3. On the rectangular coordinate system, the same point can then be plotted as 1 square root of 3. If P is any point with a rectangular coordinate xy, the polar coordinates r theta of P are given by r is equal to x squared plus y squared, and tangent theta equals y over x. For example, let's take the rectangular coordinates xy is equal to 3, 4. R will then be the square root of 3 squared plus 4 squared, which simplifies to the square root of 9 plus 16, or the square root of 25, which is 5. From there, we can find theta by knowing that theta equals the arctangent of y over x. The arctangent of 4 over 3 is approximately 53 degrees, rounded to the single degree, making the polar coordinate of the point 553 degrees. A polar equation is one expressed as a function of the polar coordinates r for radius and theta for degrees off the x-axis. For example, the equation r equals 2. We can square r to make r squared equals 4, then replace r squared with x squared plus y squared. This is the form of a circle whose center is in the origin and a radius equal to 2. A second example, theta equals pi over 6. We can take the tangent of both sides to get tangent theta equals tangent pi over 6. Tangent theta equals y over x, and tangent pi over 6 equals 1 over the square root of 3. This can then be written in slope-intercept form as y equals 1 over the square root of 3 times x. This is a straight line going through the origin with a slope equal to 1 over the square root of 3. As an example, let's take the polar equation r equals negative 4 sine theta. We start by multiplying both sides by r to get r squared equals negative 4 r sine theta. Again, we use the two equations, x squared plus y squared equals r squared, and y equals r sine theta. We replace r squared with x squared plus y squared, and r sine theta with y. We can then move the negative 4y to the other side of the equation and complete the square by adding 4 to both sides. When we factor the y terms, we get x squared plus y plus 2 quantity squared equals 4. This equation algebraically is a circle centered on 0, negative 2 with a radius of 2. Suppose a curve C is represented by the polar equation r equals f of theta for theta between alpha and beta, where both f and its derivative are continuous on an interval containing alpha and beta. Using theta as a parameter, parametric equations for the curve are x of theta equals r cosine of theta, or f of theta cosine theta, and y of theta is equal to r sine theta, or f of theta sine theta. If f prime of theta equals dr d theta is continuous on an interval containing alpha and beta, then the arc length s of C from theta equals alpha to theta equals beta is s is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. As an example, we'll find the arc length of the curve described by the polar equation r equals e to the power of theta over 2 from theta equals 0 till theta equals 2. We start with the equation of the arc length. Dr d theta is e to the power of theta over 2 over 2. Therefore, s equals the integral from 0 to 2 of the square root of e to the theta over 2 squared plus e to the theta over 2 squared d theta. Next, we take the squares to make the expression under the radical e to the theta plus e to the theta over 4. Then use the common denominator of 4 to complete the addition to get 5 times e to the theta over 4. The square root of 5 over 2 can then be removed from the integral as a constant, leaving the integrand to be e to the power of theta over 2. From here, we let u equal theta over 2, making du equal to 1/2 d theta. Then d theta equals 2 du. Substituting, we get the square root of 5 over 2 times the integral from 0 to 1 of 2e to the u du. The 2 can then be removed from the integral, which then cancels with the 2 in the denominator. Taking the integral, we get the square root of 5 times e to the u evaluated from 0 to 1, or the square root of 5 times the quantity of e minus 1, which equals approximately 3.842 units of length rounded to 3 decimal places. If r equals f of theta is non-negative and continuous on the closed interval alpha beta, where alpha is less than beta and beta minus alpha is less than or equal to 2 pi, then the area A of the region enclosed by the graph r equals f of theta and the rays theta equals alpha and theta equals beta is given by the integral from alpha to beta of 1/2 r squared d theta. As an example, let's find the area of the region enclosed by the polar equation r equals 3 cosine theta from theta equals 0 to pi over 3. We start with the area equation and replace the values to get the integral from 0 to pi over 3 of 1/2 times 3 cosine theta squared d theta. First, square the 3, multiply times 1/2 and move it outside the integral as a constant. Next, we replace cosine squared theta with the identity 1 plus cosine 2 theta over 2. Next, the 2 in the denominator can be removed from the integral as a constant. Then we split the integral at the plus sign. The integral from 0 to pi over 3 of d theta equals pi over 3. For the second integral, we let u equal 2 d theta, making du equal to 2 d theta, so that d theta equals 1/2 du. Substituting, this gives us the integral from 0 to 2 pi over 3 of 1/2 cosine u du. Next, move the 1/2 outside the integral as a constant. Taking the integral gives us sine u evaluated from 0 to 2 pi over 3. This gives us 9 over 4 times pi over 3 plus 1/2 times the quantity of sine 2 pi over 3 minus sine 0. Sine 2 pi over 3 equals the square root of 3 over 2, and sine 0 equals 0. Combining again gives us 9 over 4 times the quantity of pi over 3 plus the square root of 3 over 4, or approximately 3.33 square units rounded to 2 decimal places. To find the area of the region enclosed by the graphs of two polar equations r sub 1 and r sub 2, we begin by graphing the equations and finding their points of intersection, if any. Once the intersection points are found, alpha and beta, then subtracting the two area equations will result in the area of the enclosed section. A equals the integral from alpha to beta of 1/2 r sub 1 squared d theta minus the integral from alpha to beta of 1/2 r sub 2 squared d theta. For example, find the area of the region inside the circle r equals 8 cosine theta and to the right of the line r equals 2 secant theta. We start this by graphing both polar coordinates. Start with r equals 8 cosine theta. Multiply both sides by r to get r squared equals 8r cosine theta. R squared equals x squared plus y squared, and x equals r cosine theta. This leaves us with x squared plus y squared equals 8x. Subtract 8x and add 16 to complete the square. Factor the perfect square trinomial to get x minus 4 squared plus y squared equals 16. This will be a circle centered on 4, 0 with a radius of 4. For r equals 2 secant theta, we replace secant theta with 1 over cosine theta, then multiply both sides by cosine theta to get r cosine theta is equal to 2, or x equals 2. This is a vertical line at x equals 2. Inside the circle and right of x equals 2 is depicted by the shading. Next, to find the common points on the graph, we set 8 cosine theta equal to 2 secant theta. Divide by 8 and multiply cosine to get cosine squared equals 1 over 4. Square root both sides to get cosine theta equals plus or minus 1/2. Therefore, theta equals pi over 3, negative pi over 3, 2 pi over 3, and negative 2 pi over 3. Pi over 3 and negative pi over 3 are the obvious two intersections from the graph, so we will discard the other two. Next, we set the area problem to be the integral from negative pi over 3 to pi over 3 of 1/2 8 cosine theta squared d theta minus the integral from negative pi over 3 to pi over 3 of 1/2 2 secant theta squared d theta. 8 squared is 64 times 1/2 of that is 32. Then 2 squared is 4 times 1/2 is 2. 32 and 2 can then be moved outside of the integrals as constants. Replace cosine squared with the identity 1 plus cosine 2 theta over 2. The integral of secant squared theta is tangent theta, evaluated from negative pi over 3 to pi over 3. Next, we take 1/2 and remove it from the integral as a constant, times the 32 equals 16. Then split the integral at the plus sign, leaving the integral from negative pi over 3 to pi over 3 of d theta, plus the integral from negative pi over 3 to pi over 3 of cosine 2 theta d theta. Evaluating tangent results in 2 times tangent pi over 3 minus tangent negative pi over 3. The integral of d theta is pi over 3 minus negative pi over 3. For the cosine 2 theta integral, we let u equal 2 theta, making du equal to d theta, and then finally d theta equals 1/2 du. Substitute to make the new integral from negative 2 pi over 3 to 2 pi over 3 of 1/2 cosine u du. Tangent pi over 3 equals square root of 3, and the tangent of negative pi over 3 is equal to negative square root of 3. On the next step, pi over 3 minus negative pi over 3 is 2 pi over 3. Then remove the 1/2 from the integral, and we are left with sine u evaluated from negative 2 pi over 3 to 2 pi over 3. The square root of 3 minus negative square root of 3 is equal to 2 times the square root of 3. Now we are left with 16 times the quantity of 2 pi over 3 plus 1/2 times the quantity of sine 2 pi over 3 minus sine negative 2 pi over 3 minus 4 times the square root of 3. Sine 2 pi over 3 is the square root of 3 over 2, and sine negative pi over 3 is negative square root of 3 over 2. Simplify again to get 16 times the quantity of 2 pi over 3 plus the square root of 3 over 2 minus 4 times the square root of 3. Distribute the 16 to get 32 pi over 3 plus 8 square root of 3 minus 4 square root of 3. Combine the like terms to get the final answer 32 pi over 3 plus 4 square root of 3, or 40.439 square units. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.